Okay, welcome to this video lecture on basic surveying. Now today we are in module 12. We are starting a new module now, and this is the module on GPS. So we will begin with our lecture number 1, and this is the entire course structure that we are talking here, covered in this video lecture series. So we have already completed project surveys, and also all these have been completed now. At the moment we are in the last module of this, and we will complete this module in 3 lectures. Well, in GPS, in our first lecture today we will be talking about reference ellipsoid, because in talking about the GPS we should know about the reference ellipsoid, because the GPS observes or measures the coordinates using one ellipsoid, and then a little bit about coordinate system. Then we will be looking into the principle, the elements, applications of GPS, and advantages and disadvantages of it. So we begin with the GPS now. Okay, GPS stands for Global Positioning System. Now if you look into this, what is the meaning of this term, the Global Positioning System? It means GPS can help us wherever we are over the globe to locate our position. Now when we say position, the meaning is with reference to something, we need to define a coordinate system, and is the position in that coordinate system. So basically GPS makes use of satellites, and if this is our Earth, the satellites are orbiting the Earth at certain altitude, and using these satellites which are spread over around the Earth, anywhere wherever we can go there on the surface of the Earth, we can know our position. So this position is really very important, because this question, the question that where am I, the location is now a very, very important parameter. In many of our modern applications, we will see later on what kind of applications we need the location, where I am, or wherever we are going with the GPS, it will give me that particular location. So location means, as we are saying, the coordinate system. So before we go into the principle of GPS, we would like to see about these coordinate systems, because this is important. Unlike in the surveying, because in the case of the surveying and engineering surveying, so far we just discussed somewhere a geodetic survey, but mostly in engineering surveys we can consider our coordinate system to be a local coordinate system, unless the project is very large, and in that local coordinate system we can carry out all our measurements, all our setting out. Over here in the case of the GPS, for coordinate system we would like to define a reference ellipsoid. Now what is this? I will highlight the surface of the Earth. Now this brown color is the surface of the Earth, and it is, of course, we know, undulating. Because it is undulating, we cannot represent this mathematically. So we cannot use this as a reference surface, because it is not a mathematical surface. And instead of this, what we do, we fit, for example here, we fit an ellipsoid to the Earth, because Earth is slightly oblate. Oblate means it is not spherical. From the poles it is slightly pressed. Because it is pressed from the poles, we say it is slightly oblate. This is why we are using an ellipsoid in order to represent the Earth. So what we are doing on that undulating Earth, we are fitting an ellipsoid, which is the best fitting ellipsoid to it. So let us say this red line here is the ellipsoid, and we say this is the reference ellipsoid. because this is an ellipsoid, it's a mathematical surface, and we can define it using its parameters. Now, it is attempted that for this reference ellipsoid, its mass and center of gravity are same as in the case of the Earth. One similar ellipsoid is WGS 84, and this is the one which is used by GPS for measuring the coordinates. Well, how this reference ellipsoid is helping in measuring the coordinates? Let us look at that. So, we are defining now a system which is called geodetic coordinate system. In this geodetic coordinate system, the same ellipsoid what we saw in our last slide here, over here, the same ellipsoid I am showing now here, and this is the surface of the Earth. A point on the surface of the Earth can be represented in this reference ellipsoid in terms of, as we have written over here, phi, lambda and h. What are these? The phi, lambda and h are, this is the latitude and this is longitude and this is the normal height. What is this? Let us define here now in the figure. So, if I on this reference ellipsoid, this is the reference ellipsoid and that is the equatorial plane. That is the equatorial plane of the reference ellipsoid, and that is the other side, that is why shown by dots. Now, over here, this particular direction is, we say, IRP. IRP stands for IERS. IERS is International Earth Rotation Service Reference Pole. So, you can consider this direction as a reference pole, a reference direction which had been established by IERS. Also over here, we have a meridian. If you look at this meridian, and it will go further down because it is a full circle. Now, this meridian is also called IRM. IRM stands for, again, IERS reference meridian. So, this is also a fixed meridian. This particular meridian is also fixed. So, what we are trying to do? We are trying to define the coordinate system here, and the coordinate system now which is being defined is, first of all, I will draw it a bit thick in the same color. So, that is the direction of IRP. IRP means the reference pole, and that is another axis which is, we say, x, y and z. So, basically x is fixed, it is IRM, and z is fixed because it is along IRP. Then the position of y is defined automatically because this is a right-handed coordinate system. Now, in this, any point P, this is on the surface of the Earth. From this point P, we can drop a perpendicular or normal onto the surface of the ellipsoid. So, this we say normal. Now, corresponding to this point, we will have a meridian. So, this is the meridian corresponding to that foot of the normal, and this particular meridian will make some angle with the reference meridian. So, this angle we say lambda. So, this lambda I have shown over here. So, this is the longitude. At the same time, this particular point P, the foot of it, will make because I can draw a latitude here. So this angle is the latitude. So this particular point, the foot of the perpendicular, is being defined now in terms of phi, latitude, and lambda. Lambda is longitude, as well as the point P, the coordinates of point P can be written now as phi, lambda, and h. So this is the way we represent geodetic coordinate system. So we know our WGS84, which is used by GPS, is also a similar system, and in case of WGS84 we know the parameters of the reference ellipsoid, and the GPS makes use of this. So one system of representing the coordinates is phi, lambda, h. The another one is by Cartesian coordinate system. Now what is there in this system? Again, at the center of this ellipsoid we have the origin here. Now similarly, as we saw in our last slide, we have defined x, y, and z. Now for a point P, we can also define the Cartesian coordinates as x, y, z, where x is this and this is y, and z is the distance from equatorial plane, that is z. Now the phi, lambda, h, and x, y, z, we can determine one from the other. So basically the GPS, the very first measurement what the GPS will give us will be in the WGS84 coordinate system, and the coordinate means with reference to this geocentric coordinate system, either as x, y, z or as phi, lambda, and h. It gives me the coordinate of any point on the surface of the earth. So henceforth, whenever we are talking about the position given by GPS, we mean either of these two, and these two are, we can transform, we can get the one from the other. So in any format we can write the coordinate which is being given by the GPS. So this is important. In order to understand GPS, we should keep in our mind that yes, there is a coordinate system sitting at the center of the earth, okay, mass center, and with reference to that particular coordinate system, and we know how we defined it. Z was towards the IRP and x was towards the IRM, and then it is a right-handed coordinate system. This is how it has been defined. Well, having done this, now we will go for principle of GPS. How does the GPS work? Because so far what we understand, in the case of the GPS, on the surface of the earth we are standing somewhere with a receiver. What is a receiver? Receiver is a small device which can receive signals from the satellites. Then we have several satellites which are orbiting the earth. Now this receiver has a ability that can measure the distance. It is capable of measuring the distance from the satellite to the receiver. We will see in a moment how. So the receiver can measure the distance from itself to the satellite, and not only one satellite, it can measure the distance to multiple satellites. By making use of these distances, it is possible that we can determine this particular position, because in this coordinate system, the coordinate system which we just defined, in the same coordinate system our satellites are also positioned. At any moment we know where the satellite is exactly in that particular coordinate system. Well, having said that, so what is the principle? We will try to understand this by a 2D example. Now in the case of the 2D, let me draw a coordinate system here. Okay, this is x axis and y axis, because we are only talking in 2D. I can't draw in 3D here, and it is easier to understand this thing in 2D. Well, in this we have two known points. Let us say this is point S1 and a point S2. there is one unknown point. Let us say this is a point which is unknown, I say it is R. S1 and S2 they are known, means we know their coordinates. So we know for this x1, y1, and we know for this x2, y2. Now for R, we want to determine what are the coordinates of R, x and y. Now how should we do that? How can we determine the coordinates? Well, I said, let us say this R is the receiver and this S1 and S2 are the satellites. Well, the receiver has the possibility that it can determine its distance from the satellites. So this receiver can measure this distance, which we say as D1. It can also measure the distance D2. This distance is possible to be measured. Receiver can do it. So if it can be done, let us say if we have only one known point S1 and the D1 distance has been measured, so where all it is possible that our point R could be, because we know R is at a distance of D from S1. So all these positions, this entire circle is the position where our R could be. So we cannot really fix the position of R just by doing one measurement. So what we do, we are going for the second measurement, D2, the second distance, and if it is so, I can take again the arc here now. So from D2, satellite number 2, S2, our point R could be anywhere along this circle. Well, so what we get? We get two positions here now, position number 1 and position number 2. So our R could be at either of these two places. Now in order to find the solution for this problem, if we know that one of these positions is not possible, for example, if we take this problem to the 3D now, because what we have done so far, we are trying to understand in 2D one unknown point. To know its position, we measure the distance to two known points, and what we end up with? We end up with by solving, because right now I am doing it graphically, but it can be written mathematically also, and we can solve it. So by solution we will have two positions where it is possible that our receiver is. So one of those positions, if we know from some domain knowledge, domain means if you are on the surface of the earth, we know we cannot be up there in the sky, that kind of knowledge. So one of those positions can be eliminated, which is not possible. So basically we are able to fix by these two distances this particular position. Now what we can do, in order to take a better measurement, we take one more satellite, which is S3, and we also measure now the distance D3. So the moment we have measured the distance D3, now the third point, or rather this point, is eliminated, and we have fixed our position over here. What we will do, we will extend this now to 3D, because GPS is a 3D case. In the case of the GPS, as we discussed, there at the center of the earth we have our coordinate system, and it is possible, we will see in a moment how at any point of time, at any time t, all these locations where the satellites are, wherever the satellites are, we know all these locations, okay, everywhere these locations are known to us. Well, if we have a receiver there on the surface of the earth, there is a receiver here. This receiver is now measuring distances. So what it is doing? It is measuring distance the receiver here is measuring the distance from satellite number 1, 2, 3, 4 and so on. So, all these distances can be measured. So, if we extend our this example here, in this case we required two positions, two satellite positions S1 and S2 in order to locate our point, because we can eliminate one. So, what we will need if we are going for a 3D case, in case of the 3D we will need 3 satellites. Because you can think of it also, if in a 3-dimensional case we have a satellite here, we have an unknown point. So, this unknown point and the satellite, if we are able to measure this distance, so where all it is possible that this point could be? It is that everywhere in this sphere of this radius it is possible. So, what we do now, in order to fix our position, we take the distance of the satellite now from this reference receiver or this receiver from the second satellite. Then the sphere here and the sphere here, they will intersect. So, we have a circle. So, anywhere on that circle it is possible that our receiver could be. Now, in order to fix the point, what we do, we take the third satellite. So, again we have got one more sphere. So, this third sphere will cut this circle in 2 points. So, basically if we are using 3 satellites, finally we end up with 2 points which are our solution points, and one of these points will be not practical solution for us, because from the domain knowledge we know this point has to be accurate. So, basically by taking this into account, it is possible that by 3 satellites we can determine our position. So, here in this coordinate system, because we know the coordinates here, we know the coordinates, and by measuring these distances and doing the solution the way we are doing, we can determine this particular point. One more thing here, though, because we can eliminate one point in that case, though 3 satellites are good enough, but we would like to go for more number of satellites, because we know redundancy is always desirable. If, for example, as in this figure, we are able to see more number of satellites, so what we will do, we will take all these satellites into account, we will measure the distance from receiver to all these satellites, and then we will put all this together in order to find the best possible solution, which is coming by the least square, as we saw also in the case of adjustment. Now, couple of questions here. One question is, so far what we are doing, that we can measure the distance between the receiver and satellite. We would like to see how. Number 2, we were saying that we know where satellites are. So, that is the second question. Now, we would like to find the answer of this, how this distance can be determined, and how do we know the positions of the satellites, where the satellites are at any point in time. Well, first we will talk about the distance. So, distance of GPS receiver from satellite, we were saying that this we can determine. Now, how we are determining this? This is what we are going to look into now. Well, the satellites are sending radio signals. This is what is there. So, in this case, what is happening? In the case of the GPS, if you remember EDMI, we have discussed in one of the modules the EDMI also. In the case of the EDMI, what are the basic principle? The principle was a transmitter will transmit the electromagnetic radiation and then it will come back. So, by measuring the time of travel and by knowing the velocity of light, it was possible to determine the distance. So, distance here was C into T by 2. We can do this by phase measurement or whatever, but in this case our transmitter is sending the signal, it is sending the electromagnetic radiation. However, in the case of the satellite or in the case of the GPS, the way the signal is being transmitted, it is only from the satellite to the antenna here. From this satellite also, all the satellites are transmitting the signal, and there is no signal which is going from receiver to satellite. So, as far as the signal is concerned, the signal is being transmitted from satellites to receiver, not from receiver to satellite. So, this is not here as in the case of the EDMI. Well, if this is so, we want to determine the distance. The distance means we want to determine the distance. So, how do we measure this distance? That is the question now. Well, a very clever trick is used in order to measure the distance. What is that trick? The trick is we synchronize the satellite and the receiver. What is the meaning of this? Basically, the satellite is, if our receiver is kept here, satellite is transmitting a signal. Again, signal means these are the radio waves, and these radio waves, which are the carriers, are carrying some signals, while the receiver is just receiving this signal. Now, the question is, because receiver is just receiving the signal which is coming from satellite, and just by capturing that, it wants to determine the distance. It wants to determine, because these are radio waves, we know they travel at the velocity of speed of light. We know that, velocity of light. We know this thing. So, in order to determine the distance, we need to know how much time it took for that signal to leave the satellite and reach the receiver. If we can determine that, okay, this particular signal took so much nanosecond in order to start from satellite and reach the receiver, we can determine the distance between these two. Now, how do we know that time? So, for that, this synchronization is done. Now, what is this synchronization? In the case of the synchronization, the receiver and the satellite both are generating same code at same time. Well, what is the meaning of this? The meaning of this is, code here means, we will see the definition of code in a moment, but right now let us say, for example, I say the satellite and the receiver both start counting 1, 2, 3, 4, 5 together. So, they are counting 1, 2, 3, 4, 5 together. That means if the receiver is counting 1, satellite is also counting 1, and then it is counting 2. So, this is also counting 2, and then 3, then 3. So, basically the signal is synchronized. Now, the receiver here, because the moment it counts 1, then 2, then 3, so this 1 is traveling, then 2 is traveling, then 3 is traveling. So, what will happen? After some time, when it was counting 4, the receiver is counting 4, it will hear the 1 which was counted by the satellite. So, the 1 of satellite is reaching the receiver when the receiver is counting 4. Why? Because this 1 took some time to reach from the space to the receiver. So, now the receiver can determine the difference in its counting, which is 4, and the counting which is received here, which is 1. So, by finding this difference, which is 3, so 3 could be 3 seconds or whatever. So, what it is able to do? It is able to determine how long did it take for this 1 which was started by the satellite to reach finally the receiver. So, this is how basically the time is measured. Now, in actual practice, both receiver and the satellite, they make use of a code. We say this as pseudo random code. Pseudo random code. Now why it is called pseudo? Because it looks like random, though it is not random. So that's why it is pseudo random code, because it is something which is being generated by our program. We have written the program and it is being generated. So that code may look like or whatever. So this is, let us say, 1 and not. So we can read the code as 1 not 1 1 not 1 not 1 not 1 1 1. So basically over the carrier, because as you were saying, the satellite is transmitting the radio waves, which are the carriers. Over these carriers, this particular signal has been modulated, and the same signal is also being generated by our receiver. So our satellite is transmitting this signal, and the receiver there is also generating the same signal at the same time. So by matching the signal which is being generated by the receiver and the satellite, as we saw in the case of our example of counting 1 2 3 4 and so on. So what we are doing there, we are matching the count of satellite by the count of the receiver. So similarly here also, by matching the signal which is being generated by the receiver and the signal which is reaching the from the satellite. So basically by doing that, it is possible that receiver will determine the time of travel of the signal from satellite to itself. So if this time of travel is determined, well, it is very easy. We can then multiply it by the velocity of light in order to determine the distance. So this is the clever trick by which distance from satellite to the receiver is determined. At the same time, we were saying that we know the positions of the satellite, and these distances are measured to 3 satellites, 4 satellites, 5 satellites, any number of satellites which are visible to the GPS receiver, and the position where the receiver is can be computed. So this is one way when we are making use of pseudo random code in order to determine the distance. There are some other ways also. Now one more important thing here. So far we were saying that we will need 3 satellites for positioning. That is okay theoretically, because one of the points can be eliminated, but in GPS we need 4 satellites for positioning. Now why 4? The answer is the clock which is being used in the GPS. In the satellite, it is atomic clock. We have 4 number of clocks there, because once the satellite has been launched, in order to ensure redundancy, in order to ensure accuracy, the atomic clocks are put there. So these are very precise clocks. But this is for satellite. But here in the ground for receiver, we can't put an atomic clock here. The clock which is being put into the receiver is not that costly, is not that precise. So naturally there will be some synchronization error, because our assumption so far was the GPS signal, because why the clock is important? The clock is important, the signal is being generated as per the clock. The time is important. So in the case of the receiver, the clock which is put is not that precise. Why it is so? Because we want the receiver to be a very inexpensive one. so that it can be put in the watches, it can be put in the mobile phones, it can be put in a car, it can be put everywhere. So the receiver clock has to be very cheap. Because it is cheap, it is not precise. If it is not precise, it will have some synchronization error then. Synchronization error means, as I was saying, it is counting 1, it is also counting 1, 2, 2. If they are not synchronized, it is counting 1 while this was counting 2. Then it counts 3, it counts 2. So there is a synchronization of 1 second. So if there is synchronization problem, can we eliminate it? What will be its effect? This is what we are going to see now. Okay, let us say our satellite number 1 is here, and that's our satellite number 2. What we will do, again we will discuss this in 2D, because 2D is easier to understand. Any unknown point, let us say there is an unknown point here. If there is no error in distance measurement, we will measure the distance and we will measure the distance. So this point is being located. So basically what is happening now, this point could be anywhere because of this distance d1, and this point could be anywhere here also because of the distance d2. Now if we have an error of, let us say in distance, some delta d is the error, because if there is synchronization problem in the clock, the time measurement will be an error. If there is time measurement error, it will result in the error in the distance. So if the distance has some error, let us say delta d is the error. So what will happen because of that? Now we are measuring d1 plus delta d. If you are measuring this, let us say delta d is positive, that means we should be somewhere along this circle, not on this one, because we are measuring a distance which is d1 plus delta d. Now from the second satellite also, we will be measuring d2 plus delta d. That means we should be somewhere along this circle from S2. Now what does it do? It will shift my position from the actual position by this amount. So that's the shift. So the point P has been shifted to P dash. So this is the effect of the error. So my delta D has shifted my point from P to P dash. That's the effect of the error. Now the question is, can we eliminate it? Well, in order to eliminate it, what we do? We take a third satellite, a third point here. If you take the third satellite, and if there was no error in the case of the third satellite, let us say the third satellite is somewhere here, S1 or S3, there is no error in distance measurement. So this distance d3 will be measured like this, and we will have our arc like this, and these three intersect at this point if there is no error. Red is the case when there is no error, but when there is error, delta d as we are saying, so we will be measuring now d3 plus delta d. If it is so, we will be positioned somewhere along this arc. Now what is dodge? In case of only two satellites, S1 and S2, in that case we are able to determine our position as P dash, and we know that this P dash has error because it was shifted. Now when we are using S1, S2 and S3, are we getting any single position? No, because what we are getting as the position is now this triangle, which we say triangle of error. So we are getting this triangle. That means our point has to be somewhere in between this triangle. Now if we observe this triangle, we will find the actual position is the centroid of this triangle. So that's the actual position, which is the centroid of the triangle. So we get the triangle, we get the coordinates of these 3 points, and we get the triangle, and we find the centroid, and centroid is the point P. So what is the meaning of this? The meaning is, even if our receiver has synchronization error, which will be there because receiver clocks are not very expensive, they are not very precise. So because of the synchronization error in the receiver, still it is possible to determine the coordinate of the point accurately, because we are making use of now 3 points which we are saying here, because the example which we just discussed is in 2D, but when we take it actually to the GPS, in the case of the GPS, it's 3-dimensional problem, so we will have to add one more satellites. The meaning is, in the case of the GPS, even if there is error in the receiver, its effect can be eliminated by observing distances to 4 satellites. Because in the case of the 2D example, we saw that 3 satellites can solve the problem. So in the case of the 3D problem, we will have to have 4 satellites. Okay, a little bit about the information. This is basically more of information, and a lot of this can be get from the internet also. When we say GPS, mostly we use it as a synonym of Navistar satellite constellation or Navistar. This is a United States system. So basically the GPS is the generic name, while the GPS which is being used mostly at the moment around the world is the Navistar. In addition to this Navistar, there is also GLONASS. This is a Russian system. It is being used, but not that often, not in as Navistar. Then as well as a new system which is coming up is Galileo, and that is by European Union. So they are coming with a system which is called Galileo. So we can say 3 systems. One is the Navistar, 2 and the third, and all of these are called GPS. So GPS is basically the generic name. So the information which I am giving you right now is about Navistar. It was started in 1980s. Of course the thoughts were before that, but the process started, and in 1994 it became fully operational. The principle is that we should have some 24 satellites, so that at least 4 are above horizon, means they are visible. Visible means we receive signal from these satellites, and these satellites are put at an altitude of 20,183. Now here is the orbit and satellite positions. These satellites are put in 6 orbits with 4 satellites in each. As you can see here, A to F. This represents 6 orbits, and the numbers 1 to 4, they represent the satellite. So for example, a particular B3 here. B3 means it's in the B orbit and it's a third satellite. So we'll have B1, B2, B3, B4. So this is the constellation of the GPS satellites. Again, when I say GPS, I mean Navistar here. And as we are saying, why these satellites are positioned this way, why these orbits are given this way, why this one, why not an orbit like this? The basic idea is these satellites are positioned in such a way, and their locations at any point of time t, we should be able to see 4 satellites, or we should be able to receive the signal from 4 satellites. Of course, when you actually work in the field, you will find that very often you have more number of satellites which are visible to you. 8 satellites, 9 satellites, 12 satellites which are actually visible to you, from where you can receive the signal. Okay. Another question which we left there was, where are the satellites? Because we need this position, we need the position of the satellites here. Wherever the satellites are, we need their position, because while we are standing there on the earth with the receiver and we are measuring these distances from 4 satellites, I need to know their coordinates. Because if I know their coordinates, then only I can compute the coordinate of the point here at the receiver. Now, how do we know these coordinates? So, that is the question, where are the satellites at any point time t? Number one point which is important here, these satellites are put in stable orbits. Stable orbits means the satellite we can predict in advance, because the satellites have been put there by the Department of Defense of United States. They know where exactly the satellites are, they know at what altitude they have put the satellite, so they can do the computation for that. So, this Department of Defense is monitoring also. So, in addition to the parameters of the orbit using which the satellite position can be determined, and these positions are being computed in the same coordinate system which we talked about in the beginning. At the same time, there may be perturbations also in the satellite orbit. Because of the perturbations, the satellite will change its position from its computed position. So, from the ground station, the satellites are being monitored. So, whenever there is any perturbation, that perturbation is being recorded, and that is being recorded by Department of Defense, and this information is called ephemeris. So, this ephemeris is transmitted back to the satellite. So, the precise positions of the satellite which is there, which is being monitored, is sent back to the satellite again. Why it is sent back to the satellite? Because once the satellite is transmitting the signal which we make use of for measuring distances. At the same time, along with this signal, we have also the navigation signal which has information about the ephemeris. That means, what are the perturbations in the satellite orbit. So, basic idea is, by knowing that they are in a stable orbit, we can compute the positions, as well as by observing from the ground, we can know the perturbations in the satellite orbit. Combining these two, it is possible that the user will have precise positions of the satellite. So, the receiver will have the precise positions of the satellite by reading this navigation message, and as well as by the almanac and other information. So, once we know the precise positions of the satellite, the accurate positions of the satellite, we will apply the distances which we are observing in order to know the coordinate of the point where we are standing. Okay. Next thing about the GPS signal, because so far we are saying radio waves and carrier. Basically, we have two bands which are being used as the carrier here. Now, what is the two band means? One band is working at this frequency and the other band is working at this frequency. We say them as L1 and L2, and they are carriers. Now, why these two are used? Why not one? It helps later on, we may see, in eliminating the ionospheric error. Then this carrier is modulated, we also discussed that. So, ranging code means, as we talked about, pseudo random code is modulated on carriers, and the code is of two types. One code we say CA code. The CA stands for clear access. That means it is free, anybody can access this code. Also, it is called coarse acquisition, means it is not precise. and this modulation is done at 1.023 megahertz frequency. It's not precise, it's coarse. Well, the other code is Pseudocode. This code is available to the civilian users, share code. It is freely available. However, the Pseudocode is the precise code or also protected, also private. It is modulated at 10.23 megahertz at a higher frequency. That's why it is precise, and this code is not available to the civilian users. Rather, this code is designed for the military, because initially when the GPS started, they were started keeping the military applications in mind. So this code is a kind of protected code. Now a little information about the GPS segments. Of course, we know by this time GPS has 3 segments. One is space. Space means we have the satellites, we have their signals, and we have the orbit and other things. This is all part of the space segment. Then in the case of the control segment, the monitoring of the satellites, recording of the ephemeris, transmitting the ephemeris to the satellites, all these are part of the control segment. Then finally the user segment. Well, the user is receiving the signals on his receiver. The receiver could be handheld, could be on a car, could be on a tripod, and the user is doing all the computations in order to arrive at its location. These are the examples of the GPS. Now in these examples, the GPS can be used by keeping the antenna. This is the antenna. Antenna means something which is receiving the signal, and over here we have the battery and other parts. It can be used in combination with a total station. Also, this is the Leica GPS, which is used for geodetic surveying, or it is called geodetic receiver. Geodetic means because it is very accurate, while the GPS data can be put into a PDA, and this PDA can be connected to another receiver which is handheld, and we can carry out mapping, as we can see over here, over a GIS data, over the existing data. The additional things can be added with the GPS. So this is just an example of various kinds of GPSs which can be handheld, can be very precise, will be put on the tripod, can be put on your back, and can be used with the total station and others. Okay, having discussed all this, now we would like to see, rather we will compare the GPS with the existing techniques. Okay, now we will compare GPS with the traditional techniques of mapping or traditional techniques of location generation or determination of the location. We have understood about the surveying in our previous video lectures. We know also a bit about the GPS now. Now, what are the advantages of the GPS? One very important one is it is independent positioning. Independent means you stand anywhere and your position is being determined without any bearing on the previous position, unlike our traverse or triangulation. In case of traverse, in case of triangulation, we have a dependency on the previous position, so error may propagate here or error may accumulate, but here in this case each and every point is independent. This is very important. Then we don't have any intervisibility requirement here. If you are using GPS for survey, wherever you go, the only requirement is from the GPS you should be able to see the satellites. It is not that you need to see the other station, as in the case of again traverse or triangulation. We can use GPS in most of the weather conditions, provided you can go out and survey. unlike our land survey, because in the case of the land survey, if it is raining or if it is too much foggy, if the visibility is very poor or in the night, we cannot use the land survey. Then the survey network is designed as per the desire. Now, what is the meaning of this? In the case of triangulation, as we discussed, our network is also governed by the computations which we carry out. If our angles are not well conditioned, the error propagation will be more. So, what we want the triangulation network to have a particular shape or these angles to have some values. Because of that, the positions of triangulation stations are determined. But in the case of the GPS, we fix the position not as per this requirement, rather as per the requirement of our survey where we want our positions. So, we can see that GPS offers lot of flexibility and also it is accurate. If you go for long term observations, the GPS gives you very accurate position. The operation is less time consuming. As we discuss, round the clock we can use the GPS. One more important thing, the coordinates which we are getting are the global 3D coordinates. It is not a local coordinate system. So, anytime the survey which we have done with the GPS can be related, can be compared with any global survey. Well, at the same time, we should also see some limitations of the GPS. One, it is expensive. If you are going for very accurate GPS, we need to go for the geodetic positioning or the geodetic receivers, and the geodetic receivers will cost highly. While there are receivers which will cost only 10,000, 15,000 rupees, but the geodetic receivers will cost about 10 lakh rupees. Now, another thing, in the case of the GPS, it is important that our antenna should receive the signals. If there is a building here, so the signal is not being received, so we cannot receive the signal here. So, because of that, if the signal is not being received, for example, in underground, in forest area, thick forest, or in urban area, in that case the GPS cannot be used. Also, GPS can be used only in those positions where we can actually go and occupy. For example, if you have to measure the trajectory or the catenary of a power line, the transmission line, it is required some time. We cannot use GPS to measure it because we need to occupy the point. There are some other methods like LiDAR or photogrammetry which can be used also for inaccessible areas. So, what we saw today, we saw the principle of GPS, how do we know the positions where the satellites are, how do we measure the time of travel, and then how all this can be put together in order to determine the position. Then also one question was there that we need 4 satellites. Why? Because the receiver synchronization error can be accounted for that way. Then we saw the advantages and disadvantages of GPS. Thank you.